So blood cell formation, okay, also occurs in the marrow cavities of the bones. It's the spaces of the bones. So we've got support, protection, mineral storage, blood cell formation. Okay. And we have a variety of cells that are part of bones. We have the osteocyte, which is a mature bone cell. And you have to get used to these because there are a lot of different names and they're found in different not found in different locations, but at different times they're called by different things. We have osteoblasts, which are our bone builders. They build bone. Osteoclasts break down bone, so that's trying to show you that it's breaking down the bone. Okay? And then we have an osteogenic cell, which is our precursor to these other three types, because this is a stem cell. It could become any of these three.
Should we be familiar with what they look like?
No. Then on bones, we'll cover most of this in lab the next 2 weeks. There's a bunch of bulges, depressions, and these are sites for tendons and ligaments to attach to. They may be the site of an articulation, a junction between two bones. We make that connection. We'll have some places that are for blood vessels and nerves to run through the bone, because even though we see bones hanging out on out for Halloween, bone is a living tissue and it does have a very good vascular supply to it. Okay. So some examples is a tuberosity, which is a rounded projection. A crest is a narrow, prominent ridge. Like these, we all know what that crest is because that's when we shave our legs. It's a tibial crest. Do you shave your legs? Do you cut yourself on your tibial crest?
No, I studied them.
You study the shaped legs?
No, I studied the letter bone.
Trochanters are larger projections. These are found, we'll find this in the femur. The tuberosity we'll find on the radius. We don't look at the line, but it's a narrow ridge of bone. Tubercle, that's found on the humerus. It's a small rounded projection. An epicondyle is a raised area over a condyle. The condyle is where it makes its articulation. We'll look at those more specifically in lab. The spine is a sharp, slender projection. And then all of those are called a process. So it's anything that sticks off the bone. So not only are you going to have to know the names, you're going to have to know some of these processes. Not all of them, but a lot of them. Okay? So that makes it the skeletal system a little more difficult when it comes to lab. Yes?
You ever seen a spine and a crest?
Spine is, it's more flattened. So then we have the head, which is a bony expansion. So we have a head on the humerus, a head on the femur. Facets are found in the vertebrae. Or you mentioned the condyle is a rounded articular projection. A ramus, like this is the mandibular ramus right here. Okay, so it's an arm-like or bar bone. Further things, the meatus is a canal-like opening like we have in our ear. Okay, that's the temporal meatus in the temporal bone. It's our ear canal, basically, the bony portion of it. A sinus, we all know where sinuses are because a lot of us have sinus infections from time to time. They lighten up the skull. The fossa is a shallow basin-like depression. There's grooves, there's fissures, there's foramen. Foramen means anything that's an opening. So we'll go through these in lab, okay? And we'll talk about most of these as we go through the bones. So let's talk more about the anatomy of the bones. So we have two types of bone. We have compact bone and spongy bone. compact bone is the dense outer layer. Spongy bone looks like a sponge. Okay, think of a sponge, and you have see all those holes and crevices, and the walls of the sponge are going all different directions. Okay, that's spongy bone. It's also called cancellous bone.
Spongy is
T-H-A-T.
You got me. I got TH down.
We need to be familiar with
Sorry.
cancellous.
Do what?
We need to be familiar with the word cancellous.
Yes.
That's spongy bone.
So, yes, it's also spongy bone. Like the word cancel, cancellous. Yeah. We're gonna first look at the structure of a long bone. We do this in lab too. They consist of a diaphysis and an epiphysis. The diaphysis is the shaft, because remember, long bones are longer than they are wide. They're rounded, so the shaft of that long bone is called the diaphysis. The ends of the long bone are the epiphysis. Compact bone is bound surrounding the diaphysis, and it surrounds the medullary cavity, which is a cavity. Long bones are hollow. So they're not bone all the way through. So there's just a little bit of bone, and then they're filled with yellow marrow, which is basically fat. I hear that some people like to suck the yellow marrow out of chicken bones.
It's kind of gross. So I read if your femur breaks, it
I wouldn't suck the marrow out of it.
no, it's like the yellow marrow can get out, which is fat, and it can get to the lungs, and you can die.
Yeah, it can get to the bloodstream, because remember, bone is vascular. So it can cause an embolus, which is a fat clot.
Oh, it goes
Goes to the lungs, or it can go to the brain, cause at least a TIA, a transient ischemic attack, mini stroke. So the epiphysis are the rounded ends, expanded ends. Remember Pebbles from the Flintstones? So here's the diaphysis. And then these are both the epiphysis. This is the medullary cavity. Red marrow is where we have our blood cell formation. And then the green is the epiphyseal line in an adult or a plate in a child. BPC means before puberty.
And that's also known as growth plate.
Yes,
Would you take either one?
yes. Unless it was an old bone, because then it's not a growth plate, then it's the
A what?
epiphyseal, old bone.
Old bone?
Yeah, see, you don't have any epiphyseal plates anymore,
When you
growth
stop
plates.
growing, they turn into lines.
They turn into lines, they ossify. Because that's actually a band of hyaline cartilage. Does that make sense? So,
What age do they calcify usually?
when you go
That's
through
different?
puberty,
20 or
Oh, okay.
when you stop growing, that's why you stop growing. And men's plates grow longer than females, hence the reason men are taller. Then covering the outside, we'll put in blue, is the articular surface. And this is the articular surface, and it's made up of hyaline cartilage. So here's a picture of it, a little better than my drawing, I grant you, but if you draw it, you remember it better than if you just look at the picture. At least I did. I look at the picture, I'm like, oh yeah, that's nice, oh that's cool. Oh, what's for dinner? Oh, what was that again? I don't know. So here's the diaphysis, here's the epiphysis, here's the epiphysis. You can see all these sponge-like bone, this spongy bone, and it's filled with red marrow. Here's the compact bone. Here's the medullary cavity. You see compact, really dense bone on the outer surface. Here's the epiphyseal lines. This is not growing bone at this point, but in growing bone it's called the epiphyseal plate because it's a plate of cartilage, or the growth plate.
So everywhere else but the long bones, there's spongy bone, right? Like every other bone is.
No, all bones have compact and spongy.
Yeah. But they're spongy in all of it.
Yes,
It's
Every
filled
bone
with
has-
spongy until it gets compact.
that would be a way to say it. But the outer surface of every bone is going to be compact. So even here at the epiphysis, you'll see that right here, that's compact right here along the very edge of it. Okay, so these little bony walls, if you will, in the spongy bone that make up the compartments, those are called trabeculae. Trabeculae, yes.
On the previous slide, do we need to know the metabolisms? That one.
Nah.
What did you say?
There's an added section.
Right here,
on this
metabolisms. We don't cover it here.
Okay.
compact bone here. Well, here's a hyaline cartilage, excuse me, in blue. Here's the compact bone, and then here's the spongy bone. And we can see the blood vessels running here, so it is very vascular. If you look at this, you can see this reminds you of a slide you saw of bone. Do y'all remember me telling you there's only 2 major tissue types? Why would you answer none? What kind of tissue is this? What major tissue is this? Huh? Osseous? No. I heard someone say it. Connective. A lot of you put E, none of the above. It was connected. It asked you, what's the major tissue type here? Not specific, major. I told you there's only epithelial and connective on this test. Kind of trying to lead you towards that question. Yeah, this like. Is she done talking yet? Did she say something? I know she didn't say anything. What did I do with it?
Was it?
My clicker.
It's right here.
Ah, it's hidden. Okay, so we have that. Then this is showing you the yellow marrow. There is connective tissue that surrounds the compact bone. It's called the periosteum. We have connective tissue that protects the connective tissue, so to speak, and it attaches to the bone through these perforating or Sharpie's fibers. That's why you can't peel it off the bone, okay? And then we see these nutrient arteries, and we'll see holes that are called nutrient foramen in bones where these vessels are going in, okay? And we'll talk about the osteon here in a minute. But that's a typical structure of a long bone. So here it is set out so you can see all those structures. So outermost region is the periosteum, here in the diaphysis, followed by compact bone, and then into the medullary cavity. Here's our epiphyseal line. It's basically made up of compact bone. And here's our epiphysis with spongy bone in the center. And then the blue line here is the articulating cartilage. So, and then lining the center, which we couldn't see on the other one as well. Again, here's the periosteum. We see the Sharpie's fibers here, or the perforating, because they perforate into there. And then we see the endosteum, so there's a covering on the inside as well. And these will contain our osteoblasts and our osteoclasts, the bone builders and bone breaker downers. So even as we build bone on the outside, we take some down on the inside.
And is that modeling or remodeling when you're building and taking down?
Remodeling.
Remodeling. You said that contains osteoclast and osteoblast?
Clast.
Just blast?
Clast and blast. So the basic structural unit of compact bone is the osteon. So we can remember this from our picture that we saw, our tissue that we saw in lab. And up here is the diagram of it. I have another diagram of it. We'll come back to this. This is showing spongy bone, and so we see our trabeculae here. So the periosteum is a double-layered protective membrane. It's made up of dense, regular connective tissue. The inner side of it has the osteogenic layer, which contains both the osteoblast and the osteoclast. It's also richly supplied with nerves and blood vessels and lymphatics. Those enter in through the nutrient foramina. It's an opening. And a foramina is a fancy way, the small opening. Okay? So foramen means opening. And I always tell students at this time, they go, oh my gosh, there's too many words here. Okay, so we'll be looking at the skull. And there's one that's called the foramen magnum. Okay, that means hole. Magnum, big hole. So I always tell students, just think about those people back in their little Greek, Latin robes, standing around. Yeah, let's call that the big hole. You know the big hole I was talking about? Except they didn't say big hole. You know that foramen magnum I was talking about? Yeah, that's it right there. But we don't speak that language anymore, do we? So what do we have to do? We have to learn this old language and we hate it. Can't we just call it a big hole? No, you can't. Unfortunately, it's been set in stone. You have to know foramen magnum. Endosteum is a delicate membrane that covers the internal surfaces of the bone. So peri's on the outside, endosteum is on the inside. Now, if we look at the structure of short, irregular, flat bones, there's a thin plate of periosteum covering the compact bone on the outside. Endosteum is on the inside. There's no diaphysis, there's no epiphysis, but it's sandwiched with, they sandwich the spongy bone. So it's kind of like a bone sandwich. Got compact on the outside, which would be your bread slices, and your peanut butter in the middle. And that's your spongy bone. So here's spongy bone, here's the compact bone on the outside, and the filling of your sandwich is spongy bone. The other name for, I forgot to mention that one, I wrote cancellous up there, but I forgot to mention, the other name for spongy is diplo.
So,
I got lost on spelling that.
you said there is no endosteum, or there is?
There is. So,
It's just,
periosteum is out here, endosteum is in here.
yeah, there's just not.
It's on the inside of the compact bone.
Yeah.
But it's not a hollow cavity. There you go. Same thing, just prettier. So red marrow in infants is found in the medullary cavity of all areas of spongy bones. In adults, it's only found in the spongy bone of the flat bones, the head of the femur, and the head of the humerus, which is the proximal end of the femur and the humerus. Okay, so now we're going to go through the osteon. The osteon is the functional unit of compact bone. It's also called the Haversian system. And it consists of a central opening that's called the Haversian canal, and then it's in layers. So, like I said, it looks like a tree trunk. You always learned in grade school, you can age a tree trunk. You can't age yourself though. Would be nice, but can't. So the central area is the Haversian canal, and it contains blood vessels. Each of the rings are called a lamellae.
How do you say that?
Lamellae.
Lamellae?
And you said the Fabergé canal contains blood vessels?
Yes. And then sandwiched between, and notice that I'm putting this on the lines very specifically. These are a lacunae.
These are what?
Lacunae?
Lacunae. Okay, and the lacunae contain our osteocytes. So these mean little lakes. And they contain our osteocytes. It's not easy being green.
What's the Volkmann's canals?
We're not there yet.
Okay.
What's that noise?
It's like a muffle. Or something.
There. Make it easier to hear? Whew. Okay. So, now, let me get to the picture because Volkmann's are a little harder to understand. So, you can see osteocytes of matured cells. Ah, I forgot to write down the caniculi. And then radiating out from the lacunae, kind of like spiders, are little bitty tiny lines, and these are actually where the capillaries would be, and those are the caniculi, little canals. So keep in mind, lamellae are here. This is the matrix of the bone. Here is the osteocyte. And you can see these little lines that are reaching out. These are the caniculi. Obviously, they're cells. They need to have a way to get oxygen and nutrients and get rid of waste products. And then here's the central or Haversian canal, and Volkmann's, which you just asked about, okay, are these ones that go horizontal. So these are running the length and they're running through the center of the osteon. But obviously we have to have some way to get to the center of the bone, right? Move towards the center. And so we do that through the Volkmann's canals.
Will we go over this in lab?
Not really. But those are the Volkmann's canals. We do have a model of it in lab if you want to hold it and touch it, feel it, take it home and be, no, you can't take it home.
So, I mean, we don't really like need to worry about it a whole lot. Like,
For the test I would,
there's-
A test in here or a test?
in here,
well, yeah, I mean, so if we know
So
the
the model-
definitions, we should be for the most part okay.
I don't know what you mean by that.
Know this information, but the model will help you visualize it.
Yes,
And that's where I'm going.
so you visualize it that way. So here it is, going up a little bit. And notice that these canals, in the center of the canals are endosteum as well. Yes,
It says the endosteum lines the bony canals from the trabeculae.
uh-huh.
Is there anything else it lines with the
No.
bone? Okay, so just those canals.
Periosteum is only on the outside, basically you can think of endosteum is in the bone somewhere. Inside, endo means within. Peri means around. Does that help? Okay,
So, I mean, that's compact bone.
the osteon is the structural unit of compact bone. So we can see that, all of these. And the reason you don't always see a complete one is bone is constantly being remodeled. So these osteons are being broken down and new ones are being built, constantly. It's a living tissue. It doesn't stay the same always. And it's hard to visualize because we look at bones all the time and they're like this big solid thing. What do you mean it changes? Well, once it's out of the body, it doesn't. But we don't ever see it inside the body, so we're like, how could that change? Does that make sense?
We'll look at like semi-live bone or
No,
like fresh bone.
we do have a fresh bone for you to look at, but it's a dead bone because it's no longer attached to
I'm not
anything.
gonna cut it. Yeah, I think that's upset.
Now, the matrix of this, and I find this fascinating, one of the things that gives bone its flexibility and its strength is the fact that this is made up of collagen, and as we get older, there's less collagen in bone. So, you know, if you were if you were 5 years old and you had traffic accidents with grandma, she's probably gonna get the broken bone, and you're just gonna be like, it's a little sore, because your bones are a lot more flexible. They're not gonna break as easy. That's why children get more hairline fractures than adults, because it's harder to break something that's flexible. Does that make sense? Whereas the matrix is made up of collagen. So that gives us its flexibility. Part of the strength comes from the fact, well, part of it's the calcium phosphorus in there, but these layers that you see here, so this is a lamellae, this is lamellae. If you dissected these out, stained them, looked at the fibers, okay? The collagen fibers here may run vertical, and these would run horizontal, and then these would run vertical. So they alternate which direction they flow, they go. Does that make sense? So this goes one direction, perpendicular, back to the first direction, back to perpendicular. I think it's fascinating. Move on. So then here's the osteon you saw, here's the Iversian canal or central canal. These are the lacunae with the osteocyte inside of it. We see the lamellae, the layers that we can see that through here. Interstitial lamellae, just so you know, these are ones that are being broken down. Okay, so they're going away. We can see the fine lines that are the caniculi through here. So we can see those structures within the osteon. So osteoblasts are bone-forming cells, osteocytes are the mature bone cells, osteoclasts are the large cells that resorb, break down the bony matrix. And then the osteoid is the unmineralized bony matrix, and it's composed of proteoglycans, glycoproteins, and collagen. So that's a chemical makeup of osteoid.
So are the osteoclasts in the interstitial lamella, is that what's in there, breaking it down?
Yes, there's gonna be some in there.
So, where, are we gonna learn about osteogenic cells?
Those are just your stem cells, and they turn into one of the other three. And what happens is, as bone is built, so this is an osteon, so these are osteocytes. But as this was building this osteon, these were osteoblasts, and they entrapped themselves around with bone. And once they trap themselves around with bone, they become osteocytes. We really don't know the function of osteocytes. We just know that blasts are builders and clasts are breaker downers. Any blast cell is a builder cell. And then you just put in front of it hemocytoblast, must build blood cells. Chondroblast builds cartilage. You see what I'm saying? So blast tells you that it's making something. Class says it's breaking down something. Now the inorganic portion of bone is the hydroxyapatites, or the mineral salts, and it's 65% of your bony mass, and it's mainly your calcium phosphates. And it's responsible for bone hardness and its resistance to compression. Compression is when you squeeze it.
That's what the mineral salts are responsible for.
Yeah. And what's the technical name for those mineral salts? Apatites. 65% of that is what type of mineral salt?
Calcium.
Calcium, phosphorus.
So this is what we start to lose as we age, and that's why
No,
we start to
we lose
calcium.
collagen.
Yeah, so is
That's why our bones break easier,
35%.
because we don't have the flexibility that we need. We don't think of bone as being flexible. Okay? We really don't. But bone does have flexibility to it, and that's what collagen gives you. The hardness of bone is the calcium phosphate salts.
So would 30 to 35% be collagen?
Do what? Yes. So let's look at bone development. Most of your bones start out as having cartilage templates. So during fetal life, as you start to build your body, you start with a template that is made up of hyaline cartilage. Your epiphyseal plates, your growth plates, are made up of hyaline cartilage.
Exception, the skull and the clavicle.
Yes. And then we'll use cartilage also to increase our thickness of bone, well, not increase our thickness, but in bone remodeling and repair. So when I had that Lawrence brought up, it said there's first a fibrocartilaginous callus, but follows it, it's a bony callus. We start with fibrocartilage and then build bone to repair breaks. So there's two types of ossification. There's intramembraneous ossification, which is the, what happens with most of our skull bones and the clavicle. And there's interchondral, which uses the hyaline cartilage template. It usually begins with about 8 weeks of embryo development. Before then, it's hyaline cartilage. You're just like, what's it, a rubber chicken. Okay? So, intramembraneous develops between two fibrous membranes. Left over from that, because we haven't completely ossified, is the soft spots that you see on babies. Those are called fontanelles. So, there's a cranial fontanelle that's easily seen.
Which do those close around, is it 2 years?
They close at different times,
Just says-
but usually they should be completely closed by year. But some take a little longer, some take less.
Do
Less
boys
time.
and girls have different
That I
timeframes?
don't know. I mean, we all have them, but who closes first, if one or the other, I don't know. So there's a fibrous connective tissue on this intramembraneous ossification that's formed by mesenchymal cells. These are kind of the starting cells to form connective tissue. It begins with a fibrous connective within the fibrous connective tissue membrane, kind of like around the center, and a bony matrix is secreted into that fibrous membrane. Then spongy bone forms, and we get a periosteum, and then the bony collar forms of compact bone, and then eventually red marrow will kick in. So here's our ossification center that started. You see your mesenchymal cells here. Excuse me. Over here we see an osteoblast, and we've got the osteoblast starting to release osteoid into it. We start vascularizing and getting our bony collar. You see that along here that's going to be made into compact bone, and then here's our trabeculate of the spongy bone. So I have the stages individually here. So there's the mesenchymal cell, and within that mesenchymal cell we'll get the beginning of the osteoid matrix brought down. So we'll see some osteoblast. So the mesenchymal cells basically are differentiating into osteoblasts and start forming an ossification center where we're going to begin to form a bone. So that osteoid becomes mineralized within a few days, and again, those trapped osteoblasts now become osteocytes. Notice we have more blasts down here. They're not trapped yet, so they can continue to build bone. So that's spongy bone or cancellous. I forgot about the fourth term. Woven is the same as diploid. Lots of names for spongy bones. Don't ask me why. So we accumulate the osteoid, and it's going between some embryonic blood vessels, and it forms a random network. And because this is spongy bone, we don't see lamella yet. So it's going to be random. Remember, spongy bone does not have lamellae. Then the spongy bone condenses on the outside and becomes the periosteum. And from the periosteum, we'll then form our compact bone that's on the very outside of spongy bone. We'll end up with that plate of compact bone, and once we have compact bone, we have lamellae. Now there's two types of way the bone can grow. It can grow interstitially or appositionally. So interstitial growth gives you growth in length, appositional growth in width. So that was basically intramembranous ossification. In a chondral ossification begins about the second month of development, again about 8 weeks. And it uses hyaline cartilage as its template or models for its construction. And we're going to break down the hyaline cartilage and replace it with bone. So we get the formation of a bony collar, then we're going to get cavitation, where the hole sinks into the hyaline cartilage. Then we're going to invade it with blood vessels. And our spongy bone will begin to form. We get the formation of the medullary cavity, the appearance of secondary ossification centers, and the epiphysis. And then we get ossification of the epiphysis, but again, we'll get that hyaline cartilage going to remain, and that's going to be our epiphyseal plate, epiphyseal growth plate, which disappears with adulthood. So this goes through it. Here's the formation of the bony collar. So we see it here. Here's our primary ossification center in the center. This is called the primary because we're going to start two at the ends of the bone that are going to become the secondary, and they're going to form the epiphysis. So the primary is forming the diaphysis. Does that make sense? Starts here right in the center. So we get cavitation and we get bone laid down in there. So that's going to end up being spongy bone. Here's our periosteal bud, that's the blood supply going in. It continues to develop here. At this stage, we now have our secondary ossification centers. And then in stage 5, we'll leave some of the cartilage on the outside. This is going to be articular cartilage, the cartilage that makes the connection with the other bones, so we have something smooth to glide against. That's our articulation means a joint, so it's going to be up against the joint cavity. But then we're going to see our epiphyseal plates on either end, and so we get interstitial growth. Both the bone doesn't grow like this. So if this is the base of the bone, it doesn't go like this. It grows like this. It expands in both directions. Does that make sense? And that can be a problem if someone damages this lower growth plate. They can still continue to grow this way, but this one's not growing. So for instance, they can have one leg that's shorter than the other because of it. And that can be caused by a variety of things.
To fix that, would they just go in and do surgery on the growth plate? How would you fix that?
You can't do surgery on the growth plate. You can close the other one.
I think I have a friend that had that. I think they give them HGH.
Because isn't necessarily, when you, the problem is when you damage this,
Yeah,
it turns
messes
into
up the
bone.
function.
That's what happens, it closes it. So you can still grow this way, but you can't grow this way. So again, growth is like this, not like that. It's both directions. So you can go into the other one at the appropriate time and go ahead and close it. So they get close to being the same level. So when we look at, this is postnatal, so after birth, what's gonna happen? We've got our bones all in place, but obviously we don't stay at 18 to 21 inches in length. I think everybody's a little taller than that at this point, okay? So the growth is in length of the long bones begins with the cartilage on the side of the epiphyseal plate near the epiphysis is relatively inactive. Then based on hormones, it will start to organize itself into a pattern that will allow for really fast, efficient bone growth, okay? And we can divide that into sections. There's the zone of resting cartilage, it's not really doing much. Then we have the zone of growth, where these cells, these chondrocytes start dividing. Then they're gonna be transformed. They're gonna start to hypertrophy, which means get bigger. And because then they get too big, they die. And once they die, then we can start turning it into bone. So growth zone undergo mitosis, pushing the epiphysis away from the diaphysis. Transformation, they hypertrophy, they enlarge, that's hypertrophy, and then they begin to calcify and then they die. And when they die, the matrix, the cartilaginous matrix begins to deteriorate, and then it becomes, we start forming new bone from it. So this is a picture that kind of goes through that. So here's the epiphysis up here. Here's the hyaline cartilage. See, it's organized. See how this is kind of random? It's not organized yet. Here's nice and organized. So this is the proliferation. Notice the cells are getting bigger and bigger and bigger. So this is our transformation. So they're hypertrophy, they die, and they begin to calcify the matrix and are replaced by bone cells. So resting, proliferation, and then ossification. This is what it looks like under the microscope. The resting, quiescent zone, then here's the growth and proliferation. Then we see it's hypertrophy, it begins to calcify, they're dying, and then eventually they're replaced by the osteogenic and replaced by bone cells. Looks kind of weird, doesn't it? But they can organize themselves like that. So growth and length, cartilage continually grows and is replaced by bone as shown until the hormones take effect on it and close the growth plates. Now, bone is resorbed, and that means it goes away. And when we resorb it, especially on the internal surfaces, we're gonna build it on the outside. So if we're looking at the diaphysis, okay, the medullary cavity, we'll resorb it, we'll take it away. That's where our osteoclast would be most active, is in the medullary cavity. Osteoblast will be building bone on the outside. And bone will remodel based on the stresses that are put on it. And it's a problem that happens when people go to space. There's not as much stress and the bone starts to resorb because there's no gravity.
Which hormone causes the growth plates?
Testosterone and estrogen, the sex hormones. So here's showing you growth in length here, and then this is showing you the remodeling. So as we grow up, we're going to have to remodel this just a little bit so we see it, bone is reabsorbed on the inside and laid back down on the outside. Now, during infancy and childhood, the epiphyseal plate is activated by growth hormone. It's kind of nice. However, during puberty, testosterone and estrogen takes place and initially causes growth spurts. We've all been around teenagers, or maybe you were one at one point, and you should suddenly shot up. Okay? If you look at families, you will look at the family, maybe 10, 15 people in a what they call a family reunion picture. You will see the men are taller than the women, for the most part. Okay, there's always some exceptions because you've got your genetics and you don't know who the daddy was. You always know who your mama was. Daddy can be questionable, but you'll see that if you look at, like, I'm tall for a girl, right? I'm 5'8", just kind of tall for a girl. I'd say most of you are around 5'6", 5'5", 5'2".
Very short.
Okay, so but if you look at my brothers, both my brothers are taller than me. I have one brother that's 6'1", one that's 6'4". I have an uncle that was 6'8". So I come from genetics that give me a tall gene line, if you will. My daughter's as tall as I am. Okay? But if you look at the family lines, what happens? Yeah, I'm tall, but my brother still beat me out because testosterone closes the growth plates later than estrogen. Okay, so you get that initial adult growth spurts from testosterone and estrogen. You'll also see some changes in bones. Our pelvis is wider and flatter in females. Men's are more narrower and upright. Well, they don't carry a baby, they don't have to have a wide pelvis, okay? So we have some masculization and feminization that occurs because of those. And then they induce the closure of those plates. But again, what happens? Estrogen closes sooner than testosterone.
So if a female has more testosterone, let's do it later.
Yeah, she'd be very masculine looking though.
What about like synthetics and such?
But if she started taking testosterone in puberty, childhood, I can't imagine anybody doing that. But if she did, then they would close later. But it would have to take a lot because, I mean, women have testosterone, men have estrogen.
Not a lot.
Not a lot. But testosterone, both in males and females, is the basis of libido. Do you know what libido is? She's like, I don't know. Darla's over there going, it's your sex drive. Testosterone stimulates the sex drive. I always make a joke in A&P 2 when we go through hormones. I said that's why you have cougars. the women in menopause are like, hey, got more testosterone than estrogens, and they're like, so he's going, I'm not gonna think about my mother that way. It makes you feel any better. My daughter in high school, I think it was a psychiatry class or a sociology class, I don't remember what it was. Teacher goes, your grandparents are doing it more than y'all are. She was like, no! So,
Health is the only bone that gets masculinized or feminized, or other bones?
there's some other bones, but a lot of that has to do with the muscle mass, because testosterone increases muscle mass, that puts more stresses on the bones, and so they become thicker and heavier.
It's also your coccyx, right? Your coccyx is if you're a female, it's pointed out, and if it's a male, you're pointed in. Because birth control.
I have never heard that.
It's in the book. I've heard that before. It's like where the baby's coming out, so your coccyx is pointed in and the baby can't come through that canal, but if it's pointed
It
out.
may be a slight deviation, but it's not, I guess the way he's got it, he's got me visualizing going out, curving
No,
out,
not like that.
So,
Just like
more up and
Just
down.
curving a little more out, yeah.
And it's more up and down.
I mean, it's still
Not
coccyx,
curving
like,
out,
it's
not curving out, that's confusing, not curving out,
Yeah.
more up and down and not